So a fundamental issue with the premise underpinning Lie theory has occurred to me. So considering the S1 group, the complex unit circle is supposed to be the exponential map of the tangent space, which in this case is literally just a tangent line, which is generally treated as a real number line. The problem is that this sense of exponentiation, which is generally accepted to be an abusive notation, though not always, is actually commensurate with exponentiation over the reals. However, the full definition of this overarching type of exponentiation maps the tangent space onto the entire plane embedding S1, not just the manifold itself, meaning we've violated group symmetry. From what I gather, this issue has been swept under the rug by way of pedantic arguments that the S1 group is a multiplicative group. So, it's okay if exponentiation doesn't generalize over it nicely, but in the full definition of exponentiation, which breaks the mapping between the group and the tangent space, exponents are properly iterated multiplications, which means that the result ultimately derives from multiplication not being closed over the group, which in turn means that it's not actually a multiplicative group in the first place, as closure of multiplication is a fundamental requirement for the group's definition. This in itself, while I do doubt that it's been explicitly viewed in this way in any serious sense by more than a handful of people, if anyone other than myself, provides motivation for continuing to wrongly define exponentiation over the reals in more or less the precise way that it is in standard pedagogy. Which means this problem has high fitness, as its component parts are mutually self-reinforcing. I've also settled on curl being the adjective to denote my reasonable vector classes in dimensions of unit root -1. From what I can tell, there is no clash with the classical meaning of curl in this usage, and in many cases the meaning is actually identical or nearly so. For instance, the result of curl vector multiplication literally yields the classical sense of curl over SO3 group. Thus, rather than just having a corollary in the imaginaries, which are themselves fraught, since they're the reals in dimension of unit root -1, and the reals are an unreasonable vector class, I have, let's see, there we go, now I can scroll correctly. Curl units, basically like imaginary integers, excluding 0. Despite their seeming simplicity, this class is actually the most highly derived of the curl vector classes, a point which underpins my concerns over the generalizability of Gödel's incompleteness theorems, given that Peano's axioms derive things that look like this first, and then everything else is derived from those. Yeah. Along with other issues, the idea that the natural numbers are the most basic thing is simply unhinged. Right? It's just not the way of things. Even among people, if you look at cultures historically, the concept of numbers come quite late and are not natural. They're not that normal. Managing them, handling them, working with them is not a very normal thing for humans to do. A much more natural thing is relative magnitudes, and those don't have to come in integer relationships or rational relationships with each other. So the idea that this is the most basic doesn't work. It doesn't make sense. It's simply unhinged. Okay, and then the curl measurables. So this is the closest analog to the imaginaries, except these are not continuous, and 0 is not included. So here the measurables, what it does is it effectively takes the idea underpinning the reals and corrects the weird moves that were made that makes the reals just paradoxical and nonsensical. Right? So the measurables have almost all of the qualities that the reals are alleged to have, except that they're not continuous. Which means that if you were to have a measurable number line, it would have gaps in it. Just like if you were to have a rational number line or an integer number line, there's gaps. The measurables have gaps because it's defined correctly. Okay, and then you get the curl infinitesimals. These are the continuous values in the immediate neighborhood of any otherwise measurable or nameable value, such as the curl measurables. Right. So any value we can name. Immediately around that, you have infinitely many in all directions infinitesimals. And if that direction is root negative I, then these are curl infinitesimals. Okay? And then curl vectors. So any point along the current, because there's infinitely many, dimension of unit root negative 1, excluding 0. Right? So in like the quaternions, you have 3 of them. Right? You have the measurables, or the 1 vectors. You can generally consider it to be like the measurables, because for the most part that's what you're dealing with, unless you're taking limits. Infinitesimals really only come into play when you're taking limits, and even then, most of them don't. Virtually none of them don't. So the infinitesimals are very, very underused, which is pretty much why I think we've been able to ignore them for the most part. Anyway, yeah. So the curl vectors, it includes the curl units, the curl measurables, the curl infinitesimals, and these are properly like nested sets. You could think of it that way. If you still want to go with a set theoretic approach, you can do that. That's fine. But it's important that 0 is excluded from all of these, because 0 is always accessible since every dimension has 0. So if we establish our reference frame correctly, there is an accessible 0. There has to be. But 0 is not part of any of these vector classes, because 0 has no dimension and no magnitude by definition, and is thus not a vector. Fundamentally, all of these vector classes are derived from 0 itself. So 0 is not part of them, 0 derives them, or it's one of the fundamental components from which they are derived. So it's not a member of any of these classes, or sets, if you want to call it that. It's not part of them. It's not an item. It's not a member of them. But it's there. It's available. Once you establish your reference frame so that you can actually do any sort of work, like in arithmetic, yet 0 is available automatically. It doesn't have to be included in these groups. These groups, groups. These these classes are they're abstractions to allow us to think about things. Right? There's nothing fundamental about any of these things. These are all derived. Right? These are sort of high-level concepts derived from what's underlyingly occurring. Okay. Now this list may seem tangential or irrelevantly trivial at first blush, but its distinctiveness from the classical reals and imaginary actually allows us to much more carefully and correctly analyze the situation outlined with exponentiation. Because now, one of the problems is, say we take, using Euler's identity, and we take something like e to the I, and then it's an irrational value, like pi, or something like that. We get one solution. But if you take it to e to the I times some rational value that is not an integer, you get whatever the denominator is. You get that many solutions, right? This is interesting. If it's a whole number, you get one solution. If it's a half, like 3 halves, 47 halves, whatever, you get 2 solutions. But if it's irrational, so this is an irrational, you can think of as a fraction with an infinite denominator. Right? There's some relation between these two infinities, right? You can have an infinite numerator as well as an infinite denominator, but there's some special relationship between them, which is the value of the irrational. shouldn't you get infinite solutions? And there should be something, there's probably going to be some patterns in what that infinity looks like, which is where my unit function came from. I'm trying to suss out a little bit of detail in how that exactly works. But it's strange that conventionally we're just like, yeah, e to the I pi, that's just -1 and nothing else. Whereas if it was rational, you would get multiple solutions. So, yeah. So this allows us to handle infinitesimals because they're just explicitly there now. We can see them.